I think everybody here probably is familiar with what he does, but let me say a little bit about that in any case. He got his PhD at Cornell University. I just learned that his PhD advisor there, no surprise to me knowing that Venkat was at Cornell, that Venkat was indeed the PhD advisor of Ganesh. And he is now at the University of Bristol in the mathematics department. He's very well known for his contributions to the mathematics of communications networks. He's worked extensively in the area of applied probability, large deviations, related issues. Works on distributed control problems and distributed algorithms and so forth. And I'm very pleased that today Ganesh is going to tell us about secure connectivity of wireless sensor networks.
Thank you, Peter, for the introduction. It's a pleasure to be back in Cambridge, and I'd like to thank the organizers for inviting me. Can you all hear me? Yeah, okay, great. Okay, so this is work I started with Manjunath at IIT Bombay and his student Santana Krishnan when I was visiting there last year. It's continuing on from some work of Arman Markovsky that was mentioned when he was here for the first workshop in this series. So we had a brief chat about that at the time. So I'd also like to acknowledge the debt to the first workshop, and this is continuing on work from that period. So I'll start by describing the problem. What we have some number of nodes n, which is going to be large, distributed in some region. Let's say it's the unit square. And as usual in such problems, I'm going to pretend that the square is wrapped around itself into a torus, so we don't worry about continuity, about boundary effects at any point. We have cryptographic keys. There's a pool of p cryptographic keys, and each node is assigned some k of these keys at random. Okay. And then when can two nodes talk to each other? They can do this if they are close enough within some communication range R, and they also have to have a key in common in order to communicate. So that's the model, and that model induces a random graph on this set of nodes. And we want to ask when this random graph is connected, when it's possible for any two nodes in this set to communicate with each other through some intermediate nodes. I'm coming to the background. Yes, so I thought it's good to start with a concrete problem statement and then come to the background. Okay, so the background is that well, it was about trying to create a scheme for secure communication over ad hoc wireless networks. The idea is that you scatter these nodes over some terrain, possibly in a military situation where there's an adversary who's trying to listen in on your communications, and you want to be able to communicate without it being possible to be overheard, and your adversary may also capture some of these nodes and so on. So you want to be robust to these things. And that was the motivation for Eschenauer and Gligor to propose this particular key distribution scheme back in 2002 of simply assigning, generating and assigning cryptographic keys at random to these nodes. The first analysis of this that I'm aware of, it was started by, this was done by Arman Markovsky, as I mentioned, and his PhD student Osman Yagan. And they considered this without taking the geometry into account. So assuming that all nodes can see each other, they are within close enough range that the parameter r that we mentioned doesn't come into it. So you just have to worry about the size of the number of keys each node gets. And they proved the following theorem. So they said that, they showed that if, so k is the number of keys you get and p is the total number of keys. And from that, the probability of an edge between two nodes that you share a key is roughly k squared over p. And they showed that if this is a little bit, so that's the edge probability. So n times that is the mean degree. Okay, so if the mean number of neighbors you have is a little bit bigger than log n, then the graph is connected. If it's a little bit smaller, it's not, which is what you expect from what we know about the Erdős-Renyi random graph. The difference, of course, is that this is there's a lot more dependence here. So in the Erdős-Renyi graph, the edges are independent. So I think that's the next slide. So I might as well go there. Okay. So the intuition is that if the edges were independent, then you have the Erdős-Renyi random graph, and this is the connectivity threshold. But here, of course, if there's an edge between nodes A and B and between B and C, that says that A and B share a key, B and C share a key, so that makes it a bit more likely that A and C share a key. So the edges are not independent. Okay, so that's one background for this kind of problem. The other bit of background comes from the study of random geometric graphs. So here you have, again, n nodes uniformly distributed on the unit square, and then you have some probability that, well, nodes are connected depending on how far apart they are from each other. And you have some edge probability G for two nodes at distance x from each other being connected is given by G of x scaled, again, by this parameter R that somehow depends on n. And the best known example of this is the Boolean model, where you are connected if the distance is smaller than something. So after scaling, if the distance is smaller than r, the nodes are connected, and otherwise they are not. And this, in the case of this model, again, there's a threshold for connectivity. This was shown by Matthew Penrose. And again, it's at this mean node degree of log n. So the expected number of neighbors is if it grows faster than log n, you're connected, and otherwise you're not. Okay, and the more general case that we introduced, where G is some general function and not just 0 or 1, that was studied in recent work of Mao and Anderson. And what they showed is that you get similar results. There are further conditions on G that you need. And the way they phrased the result, they were looking at an infinite model rather than a finite model. So you have a Poisson point process on the plane. And what they said is that if you look within within some bounded region and you want to ask the question, are there small disconnected components within this or not, then you have a similar threshold for that. Okay, so that's the kind of, those are the kinds of problems that have already been studied. So in the case of, without the geometry, the case of the key graph has been studied, and with the geometry, the edges are independent in the Mao and Anderson model. So what we are studying here is having this geometric constraint on when there are edges, and also having this constraint that you have to share a key in order to have an edge. So it's an intersection graph of those two things. And what we are able to show in this setting is what you would expect again, that, well, it's a bit weaker than that, which we hope to sharpen up. What we are able to show is that if your if your mean number of edges is log n minus a little bit, you should think of no, is that should be log n minus c, I guess. Yeah, so if your edge probability is a bit smaller than log n, then with high probability the graph is disconnected. And if your mean number of edges is bigger than log n, so we are only able to show this for being bigger by a multiplicative constant rather than additive, so it's not quite as sharp. But if you have 1 plus epsilon log n edges, then you are connected with high probability. Okay. So those are the results. And well, I'll give you a sketch of the proof and some of the intuition behind the results. One direction is easy, so we'll start with that. The easy direction is to show that if you have fewer than log n edges on average, then with high probability the graph is disconnected. And this uses the same approach we use in the geometric random graph or the Erdős-Renyi graph, which is to look at isolated nodes. If there's at least one node that's isolated from everything else, then clearly the graph is disconnected, and that probability is easy to calculate. So for a node to be disconnected, the edge to each of the n-1 possible other nodes should be absent, which is just some quantity to the power n-1, and that gives us the probability that a given node is isolated. So if that probability is of order 1 over n, then taking the union bound, you expect that there's at least one isolated node. Okay, so that almost gets us there, but that's not quite enough. Even if the expected number of isolated nodes were growing to infinity, it's not obvious there is an isolated node. So you have to also control the variance or something else to show that. So what we do is we use the Bonferroni inequality to say that, well, you look not only at the probability that a single node is isolated, but also that pairs of nodes are isolated. And then you have a lower bound on the probability that there's at least one isolated node. So that's the approach. It's again, if you have done similar things for Erdős-Renyi random graphs, this might be very familiar. Yeah, so which for many of you is hopefully the case. Okay, and then we can estimate probabilities of pairs of nodes being isolated, etc. It's not difficult, so you have to condition on how far apart they are and go through the calculations, so I won't go through the details. Okay, so the lower bound is harder, and it's useful to recap the analysis for Erdős-Renyi random graphs, because we are going to follow the same sort of ideas, but in case you're not familiar with that, I'd like to remind you of how it's done in that case, and then the rest is easier to follow. So in Erdős-Renyi random graphs, how do we show they are connected above the threshold? We look at we try to upper bound the probability that there's any disconnected component. So we started talking about isolated nodes. We bound the probability that there's an isolated node anywhere, or an isolated subset of connected subset of size 2 that's isolated from everything else, or subset of size 3, and so on, and add them all up. So that's the approach, and we show that all these things vanish. And we are going to take the same approach here. Except we aren't able to make this go through at all scales. So we are going to split up the problem, and we are going to use different bounds on different scales. So let's see, what do? We take this unit square on which our points are located, and we are going to break it up into little squares of size r over square root 2, and the reason for that choice is then any two nodes within that square are within distance r of each other. So within one of these little squares, everybody can see everybody else. And we don't need to worry about where they are. We can pretend it's an edge. Well, we can ignore the geometric aspect. And then we'll look at what kind of isolated nodes or small components there are within these little squares, and then try to put them together. Ideally, okay, if everything worked out very well, what might happen is that none of the little squares have isolated nodes. Then we are done. Then everything has to be one big connected component, and we are done. Unfortunately, that's not going to happen. So some of these will have isolated nodes or small components, and so we have to find some way of dealing with that. Okay, so I've already said this. So we look within these little squares and ask locally, are there things that are disconnected? I want to emphasize again, something could be disconnected locally if you look only within one of these little squares, but globally it could be connected to something outside because your range is R, and I've taken a square that's smaller than size R. So you could be connected to something else outside, and that's what is useful to ensure that the whole thing's connected. Okay, and so our proof, I'll just give the outline of the proof, and then we'll drill down into how we prove each of these little parts. So what we can show is the following. If you look at the big square as a whole, we can show that there are no small disconnected components anywhere within it. If there's anything at all, either it's fully connected or there are very big components which are separated from the rest. There's nothing of size big O of 1. There's no constant size components. Also, if we look within each of the little squares, we can show that there are no big disconnected components, but there may be small ones. There may be isolated nodes or things of size 2 or 3 up to 6, and it will become clear where the 6 comes from later. There may be small disconnected components. So how could the whole graph fail to be disconnected? So two things could happen to these small disconnected components. They get connected to the giant component in the neighboring cell, in which case things are fine. Or they get connected to another small component in the neighboring cell. But then it's still small, unless this keeps happening repeatedly and it becomes big. For that to happen, somehow, if you look at these little squares and the little components inside them and look at the edge probabilities, that process should percolate. And we'll show that can't percolate. So that's the idea of the proof. Okay, so now a bit more into the detail. We have capital N nodes in the big square. The communication range is R. There are P keys in total, and each node gets K of the keys. We'll introduce one more term, little n, which is the number of nodes within communication range, expected number of nodes within communication range of any single node, and little p is the edge probability. Okay, and there are some technical assumptions which basically say that if you look at one of these small squares that we defined, there are many more than log n nodes in each of these squares, and so pretty much uniformly over all of them, the actual number, the random number of points concentrates around its mean value, and so we can ignore those fluctuations. And the mean value is n over 2 pi. Okay.
You just denoted little n is.
So little n is so if there's a node sitting here, there's a circle of radius Rn within which it can communicate, and little n, R of capital N, sorry. And little n is the expected number of nodes within that circle. Okay, so let's just do some heuristic calculations to see what the intuition is, and then we'll talk about making it rigorous. For now, we are pretending that it's an Edersheim graph within this little square. There are about little n over 2 pi nodes because the square is smaller than the circle. So inside this circle, we have put in a little square. And there's an edge probability k squared over p between any two nodes. Now, if you calculate the mean degree, it's not, well, it's something times log of capital N. And what you actually need is log of capital N in there to give you global connectivity. If you had log of little n nodes, any given cell is very likely to be connected, but there are a lot of such cells, so some of them will almost certainly have isolated nodes. So log of capital N is what you want, but you don't have that. C could be just a little bit bigger than 1, So you have only 1 over 2 pi times what you want. So if you pretend this an Erdős-Renyi random graph and do the calculations, you'll see that you might get isolated nodes, you might get isolated small components, but all these small isolated components you get will be smaller than this 2 pi. So you won't, you are with probability going to 1, you won't see anything of size 7 or bigger that's isolated. And that's if it were Erdős-Renyi, which it isn't, but we can show the same thing, taking the dependence into account. And how do we do that? Okay, the way we do that is by conditioning on the number of keys they share in common. So what we want to do is get a bound, an upper bound on the probability that there's some set of m nodes which are connected but isolated from everything else. Each of them has k keys. If there were no overlaps between the keys, there would be mk in total, but there might be fewer than that. In fact, there should be fewer than that if they are to form a connected set. They should have at least m minus 1 keys in common, because you need at least m minus 1 overlaps for them to be connected. And then none of the other nodes should share one of these keys. So these are the probabilities we have to estimate. This isn't enough. If these two things happening is necessary but not sufficient, but it gives us a bound in the right direction. Okay, and how do we bound this? So what we want really is a tight bound that on the probability that these m nodes have mk minus j keys between them. And approximations are easy to get, but they aren't good enough. We need quite tight bounds, and what I'm going to say is how we get those. So first we can make the calculation a bit easier by pretending that we choose these keys with replacement rather than without replacement. And now, as you sequentially keep choosing these keys, what's the probability that at the ith step you pick up a key you've already picked? You might, there are at most, I might, at I plus 1 step. So there are at most I distinct keys you've already picked, in which case this probability is I over P. It could be smaller than that, but it's at most that. So that's the probability that you see that you have a collision, that you see a key you've already seen before. And what we want is a bound on the probability that you see j such collisions. Okay, and here we use a very, very nice result of Hoefting. So what we have is these, we can model these collisions as independent Bernoulli random variables. They are not independent, but they are dominated by something independent. And there's some probability pi that there's a collision at the ith trial, and what you want is a bound on the total number of collisions. It turns out that the sum of independent Bernoulli random variables, if you look at a Poisson random variable with the same mean, then that dominates the sum of the Bernoullis in the convex stochastic ordering. So that says that for tail events, the probability of seeing more than j collisions for the y random variable is smaller than for the Poisson random variable, for which we know how to calculate things exactly. And that was the key step in making that calculation easy. Okay, so that's yeah. So that pretty much helps us to get a bound on on the probability of getting a component of some size m, which is connected but separated from the rest. And that pretty much completes the analysis of what happens within a small square. Okay, and then we go to the big square, and again we want to look at similar events. What's the chance that you have m nodes forming a connected component which is isolated from the remaining nodes? And the way this can happen, there has to be some permutation of the nodes so that each of these nodes is connected to the next one, and we have to condition on all possible numbers of keys that they share, and then these M nodes have to be disconnected from the remaining nodes. So again, the first term is easy to calculate. The second term I've told you how to bound. And the last term, conditional on the keys, it also depends on where the nodes are located, which brings in dependence, and that makes it hard to calculate. But we can again ignore the dependence by pretending that the nodes are sitting right on top of each other, which is somehow makes this event of disconnection least likely. So we can get a bound by doing that. Okay, and that's pretty much all there is to this. So the point, I guess, is that there are a lot of sloppy bounds going on here. That's why there's no single approach that worked for us throughout the square. So if M is fairly small, pretending that they are all sitting on top of each other, it's sloppy, but it's not too sloppy, and you can get bounds which are good enough. But for large enough M, that stops being good enough. So essentially, we had to much of the problem in this case comes from the dependence. So there was no one method that worked uniformly at all scales, and we had to use different sloppy bounds and approximations on different scales and stitch them together. Okay, so I've told you what happens on the small square and the big square, and then it's just a matter of putting them together. I already mentioned this earlier. So what these bounds tell us is that most of the nodes belong to a giant component. If you look just within a square, some of these squares contain small disconnected components. So what might happen to these? These might get picked up by the giant component in the neighboring cell, or they might stay isolated, or they might have edges to other small components. Staying isolated is not allowed because we know there are no small components overall. An edge to another small component in a neighboring cell is possible. But if a big component were to be built up this way, the edge probability would have to be above the percolation threshold, which for the square lattice is 1/2. But in fact, we can show by counting the number of these nodes that the edge probability is close to 0. It's nowhere near 1/2, so this can't percolate. These small components must necessarily get picked up by the giant component. Okay, so that was all. It's a self-contained problem, and that was the proof. Thanks.
Questions?
Have you thought about the giant component phase transitions?
No, this turned out to be a lot messier than we expected when we started on this. No, we haven't thought about that. Or about other things like K connectivity and so on.
Yes.
So the parameters you're looking at, I guess, like the Lovash local lemma framework doesn't hold for those parameters.
We didn't try that very much, but did think about that. Steinchen wasn't good enough because we need a bound that works in the tail as well.
Thank Ganesh again for a very nice talk.